All right, welcome to your lesson on geometric mean. The word mean in this instance refers to the mathematical definition, which is associated with average. Now, average up until this point, you've always associated with what is called the arithmetic mean, where you add up all of your numbers and then you divide by however many you have. This is going to be the geometric interpretation of that. So it has something to do with our objective here, which is about finding missing links in similar right triangles. So in a previous lesson, we talked about similar polygons, and for two polygons to be similar to each other, what has to be true? They have to have congruent corresponding angles, first of all, and they also have to have their corresponding sides have to have the same ratio, which means they're proportional to each other. And we're going to apply those things to right triangles specifically. Before we do all of that, let's take a look at this image. Chances are you have a television or two in your house which has an widescreen aspect ratio of 16 by 9. So this is the standard high definition aspect ratio. If you don't know what aspect ratio is, if you were to take the longer length of your television and divide it by the shorter length here, this vertical one, and reduce that fraction, you would get 16 by 9. Every single widescreen high definition television would reduce to 16 by 9. But this wasn't always the case, of course. Your parents probably grew up with a television with an aspect ratio of 4:3. So here, again, this time, if we were to take the longer length here, divided by the shorter length, it would reduce to 4/3, or 1.333. Now, it might just so happen that you've watched an older television show, maybe streaming on some sort of a streaming service, and you see these black bars on the side because it was originally broadcast in a 4:3 aspect ratio, and it's trying to fit it onto your screen, which is much larger than that. Unless that streaming company, for whatever reason, is stretching it to fit your screen, in which case it looks like total trash. Okay, but most movies, though, were filmed in a much, much larger, much wider aspect ratio, and the widest of those is CinemaScope, and it looks like this. So CinemaScope has an aspect ratio of 2.35 to 1. Now, back in the days when we had televisions, the 4:3 televisions, and you wanted to buy yourself a copy of a movie, you had two options. One of them was a letterbox, which is basically what we're seeing here, where it would put black bars on the top and the bottom. But it would have to shrink down the image so that it would fit on your screen, right? This is what we were supposed to be seeing, but we couldn't see all of that on our screen, so they had to shrink that thing down. So not a lot of people were happy about that. Okay, so then your other option was to take that CinemaScope and only use a portion of it. They would chop off part of the image so that it would fit on your screen. And not a lot of people were happy about that, especially directors, because they filmed it in a particular way. I want you to see this whole entire image, and you've just chopped off part of it. And you'd also miss sometimes some of the action. So in this case, if you look at this particular image, it would take this rectangle and chop it off. It would take this rectangle and chop it off, and only give you this center rectangle right here, which was called full screen. Okay, so what the heck does that have to do with similar right triangles and geometric mean? Well, here, let me add in a little diagonal here, and you can see whenever I take a rectangle and I add in a diagonal, it makes a couple of right triangles, and then I'm going to throw in this extra line here, and that's an altitude. And this altitude with those right triangles has something to do with geometric mean. As a matter of fact, that's how this guy named Dr. Kearns Powers came up with this aspect ratio of 16 by 9 back in 1984. All right, so then, speaking of altitudes, let's review just a little piece. An altitude is a segment that's drawn from a vertex, and it has to be perpendicular to the opposite side of the triangle. Every single triangle would always have three of these altitudes. The word altitude is associated with the height of that triangle. Height and a base of a triangle, of course, they have to make a right angle. Now, when we're talking about an acute triangle, like this one, H, F, E, all our altitudes are on the inside. So here's one that's highlighted here, but it's not the only one. We could also draw one from H to this opposite side here, or from F to this opposite side, and all of them would be on the inside. Whenever you have an obtuse triangle, though, some of them are on the inside, but not all of them. Like, for example, from O to this opposite side, I can make a right angle. However, from M to the opposite side, if I tried to draw it on the inside, it wouldn't make a right angle. So what we have to do is extend out that side so we can bring this altitude over, right? And the same thing happens with this obtuse triangle right down below it. Right triangles, though, are special. Right triangles are special because two of the sides are already altitudes. This J to I, from J over here to this opposite side, already makes a right angle. It's an altitude. Same thing from K to I. It also makes one. But there's one more. Here, let me come back over here so I can draw it in here for you. Boop. And there's one more. And this third altitude, stay, is right here. And it makes, oh, that was trash. Okay, let me try again. There we go. And it makes a right angle with a hypotenuse there. All triangles, like I said, have three of them, and they all meet at a single point, a point of concurrency that's called the orthocenter. Okay, so specifically for this lesson, this is the diagram that we're concerning ourselves with. So the altitude that's drawn into a right triangle, and notice that whenever you do draw in that altitude, it creates some other triangles, specifically some other right triangles, okay? So when we have ourselves a right triangle, in this case I have this right triangle ABC, it has three altitudes just like any of them. One of those altitudes is one of your sides, it's AB. The other one is BC, because both of those make right angles with the opposite side. But there is one more, and that altitude extends from the right angle B and then makes a right angle with a hypotenuse here. So in this case, we'll call that thing BD. And notice that whenever we draw in that extra altitude BD, it creates two other right triangles. I've got triangle ABD over here on the left-hand side and BDC over here on the right-hand side. And there's some special relationship between those two right triangles. So let's take a look at that in an investigation in the next video.